Welcome all of you in this lecture. Today we will discuss double integration method and Macaulay's method. These two methods are very important to find out deflection and slope at any point in a beam. After the concept discussion, we will solve one problem based on Macaulay's method. So let's start. First is the double integration method. Let us say we have a beam. This is the beam and there is some support conditions and there is some loading on it. At any distance x from the support, let's take out a small piece of length dx. From the bending formula, we know that m by I is equal to sigma by y is equal to E by r, where 1 by r is known as the curvature, E is the Young's modulus of elasticity, sigma is stress, m is the moment, and I is the moment of inertia. So from here we get 1 by r is equal to m by ei. 1 by r is known as the curvature. Mathematically, the curvature is defined as d2y by dx square divided by 1 plus dy by dx whole square to the power 3 by 2. If we see the deflection pattern in a beam, then we will find the slope dy by dx at any point. This slope dy by dx at any point is very small. So we put dy by dx is equal to 0, then what we will get is m by ei is equal to d2y by dx square. Please note that here there is one assumption, that is dy by dx is very small. We can write this equation as ei d2y by dx square is equal to m. If we integrate both sides, then we will get ei dy by dx is equal to some constant of integration plus integration of m. If you integrate once again, then you will get ei y is equal to c1x plus some constant plus integration of whatever that we get from the previous step. This all integration is performed over the length L. So to calculate the deflection y using double integration method, where is the double integration here? This is the double integration method. Is known as double integration method. Now what is this Macaulay method? Let's say we have a beam. These are the support conditions. And we have different types of load. One load is here, other load is here. There is some other load, W1, W2, W3. Now you can see this beam is divided into a number of sections. Like you can see first section here, second section, third section, and fourth section. So a single moment equation cannot define moment at all the sections, right? So in Macaulay method, we define one equation and we modify it such a way that only one equation, moment equation, represents bending moment in all the sections. In this method, we have to take the last segment of the beam. So here this segment is the last segment. So we will take section X in this segment. Let's say this is the X and we write moment equation M as, let's say here we have direction RA and RB, then we can write M is equal to RA into X minus W1 into this distance is B and this is C. From here to this is C. W1 into X minus A minus W2 into X minus B minus W3 into X minus C. And the condition that we apply here is, if any term, either this term or X minus C term is negative, then we replace it as 0. Like if X minus A, if this is negative, then X minus A is equal to 0. Similarly, X minus B is negative, then we replace X minus B is equal to 0. Similarly, X minus C is equal to 0. This way we will get the moment equation. Now we will solve one problem related to Macaulay's method. This is the problem. In this problem, the beam type is simply supported beam and it has an overhang of 1 meter. Support to support distance is 8 meter given here. It carries a UDL of 6 kN per meter at certain distance from 1 meter to 5 meter in this region, right? And we have a 8 kN load applied at the tip of the overhangs, and what we have to determine is deflection at C and maximum deflection in this range. So let's start. The very first step is calculation of reaction force. First we will write the equilibrium equation. Force equilibrium. Summation of all the force in vertical direction is equal to 0. So what we can write? Reaction at A is RA, reaction at B is RB. So all the upward load will be equal to the downward load. So upward load is RA and RB. This will be equal to downward load. Downward load is, we have a UDL in 4 meter length, this length, so it will be equal to 6 into 4 and a point load in downward direction of 8 kN. 8. So RA plus RB is equal to total of 32 kN. This is our first equation. Now we have to write the moment equilibrium equation. Summation of all the moment at point A should be equal to 0 because point A is hinged point. So let's write. RB into distance of point B from A is equal to 8 minus moment of this point load 80 kN. It will be equal to 8 into distance from point C to point A, which is equal to 8 plus 1 is equal to 9. Again we have to write moment due to this UDL, this UDL. Moment is equal to total load into distance of the CG of the load. Here total load is equal to 6 into 4 and distance of CG load from point A is equal to, this is the CG, Total length is 4 meter, so this length will be equal to 2 meter. Total length is equal to 1 meter plus 2 meter, 3 meter. Into 3 is equal to 0. If you solve this, you will get RB is equal to 18 kilonewton. This is second equation. From first and second equation, we can calculate value of RA. It will be equal to 32 minus 18, 14 kilonewton. Now we will take one segment at the extreme end. Here the extreme end is BC. So let's take a section here in a BC. This is the X distance, and we will write the moment at X. To simplify this, what I am doing is I am applying one UDL from this point to point C and other UDL in opposite direction to nullify this up to C. Now moment at distance X can be written as, please note, it will be equal to RA into X minus moment due to downward UDL. It will be equal to W L square by 2. W is given as 6. Length is X minus this distance, X minus 1 square by 2. Again, I am writing moment due to the UDL, which is in upward direction. It will be equal to 6 into X minus 5 square by 2. Why 5? Because this distance is 5 meter. Moment due to that RB, it will be equal to RB into this distance, X minus 8. If somebody asks what is the moment in this region, then you have to say moment in this region is only up to this part. And what is the moment in between this region? From 1 meter to 5 meter. Then you have to say moment from starting up to this point. Again, if somebody asks what is the moment between this region to this region, then it will be up to this part. And if somebody asks what is the moment in the last segment, then it will be from a starting point up to that last segment. Now we have to apply the Macaulay method. This mx is written as per the Macaulay method, and that Macaulay's method uses double integration method. So we will apply that double integration method. As per double integration method, ei d2y by dx square is equal to moment. Here moment is Ra into x. Ra is 14, so 14 into x minus, we simplify this. Rb is 18, so we have to write 18 into x minus 8. Now to get the slope, we have to integrate that equation. On integrating, what we get is ei dy by dx is equal to, we have to write this part everywhere, we have to integrate 14x, it will be equal to 14 into x square by 2 means 7x square minus 3 into x minus 1 whole square, it will be equal to 3 into x minus 1 whole cube by 3. So 3 will get cancelled out, it will be equal to x minus 1 whole cube. Again we have to integrate it, it will be equal to x minus 5 whole cube, and the last part it will be equal to 18 into x minus 8 square by 2. Now we have to also write constant of integration. Let's say it is c1 and this equation is equation 1. Again we have to integrate the equation 1. We will get eiy is equal to 7 by 3x cube plus c1x, constant of integration c2, so the first term, minus we have to integrate that second term, x minus 1 whole cube will equal to x minus 1 whole 4 by 4 plus x minus 5 whole 4 by 4 plus 3 into x minus 8 whole cube. So this is the second equation. Now how to find this c1 and c2? This c1 and c2 can be found out using the boundary condition. For a simply supported beam, we know that the deflection at point A and the deflection at point B is equal to 0. So here boundary condition is deflection means y at x is equal to 0 and deflection at x is equal to L is equal to 0. These two are boundary condition for the simply supported beam. But if we have a cantilever beam, in this case we know the slope at this point is equal to 0. Deflection, if there is any load, deflection pattern would be like this. Here slope is 0 and deflection at this point is 0. So boundary condition will be equal to y at x is equal to 0 and slope dy by dx at x is equal to 0 is 0. These two are boundary condition for cantilever beam and these two are boundary condition for simply supported beam. Here in this question we have a simply supported beam, so we will apply this boundary condition. Boundary condition at x is equal to 0, y is equal to 0. So what we'll get, this term will be equal to 0 is equal to 4x is equal to 0, 0 plus c2 minus 7 to the power. So these two are equation 2 and equation 1. First question, we are being asked to calculate deflection at the end of overhang portion. So y at x is equal to 9 is equal to, if we put all the value then we will get 52.43 divided by EI. This is the answer. Again we have to calculate the maximum deflection between A and B. So wherever there is a maximum deflection, the slope is equal to 0. So to calculate maximum deflection dy by dx is equal to 0. Now we have to do trial and error to calculate this location where there is a maximum deflection. First we will assume, let's say the maximum deflection occurs in between x is equal to 1 to x is equal to 5. So we have to take this expression up to this point, because if we put x is equal to 5 from this expression, it will be negative, so we don't have to take that. If you do so, you will get x is equal to 3.7228, and again put that value of x in equation 2 to get maximum deflection. So y max will be equal to 179.43 by EI. Put the value of E and I and you will get the required answer. So, to solve this type of problems, what steps you need to follow? The first is calculate reaction force, Ra and Rb. How you will calculate this? By equilibrium equation. Then the second step is write moment at x. Choose the section x at extreme segment. And third is write double integration equation like m by ei is equal to d2y by dx square. Then again integrate 2 times and get expression. Then apply boundary condition. Put the value of boundary condition in the above equation and you will get an expression for dy by dx, that is the slope, and y at any point x. So this is the method. Here we come at the end of the lecture. I thank all of the students for their patience and some Excel team for writing all the questions on the slide. Thank you very much.